Hello everyone! In this video I'm going to completely remake the solar system. That is, its structure will be radically changed. You'll see where the planets will orbit now, how they'll change, and more. All of this will be demonstrated using the Universe Sandbox simulator. Let's get started. And I'll begin by making Jupiter a star in this system. I'll set its mass to 79 times the mass of Jupiter. This will indeed be just the absolute minimum threshold for a red dwarf star. Right now it's so dim, but trust me, we just need to fast forward time and then it'll ignite. Next, I'll have to completely remove the entire asteroid belt and even all the planets. I'm also deleting the various outer planets and the dwarf planets as well. Everything's been deleted, and at this point, only Jupiter and the Sun remain in the system. Now I'll select these two objects, balance the system with just the two of them, and create a barycenter. Now you can see how Jupiter will ignite. Here in fact, the temperature keeps rising and rising. An incredible amount of time passes. I'll speed it up even more, and as we can see, Jupiter ignites and turns into a red dwarf, a full-fledged star. As a result, the surface temperature of Jupiter's star reached 2842 degrees Celsius. And here we can see that this star, a red dwarf, is emitting coronal mass ejections. So now we actually have a binary star system here, and time was fast-forwarded while Jupiter was igniting. And as we can see, this didn't affect the orbits at all. Overall, everything is stable. Next, I'll place Neptune, which will orbit the barycenter at a distance of 15 astronomical units. As you can see, Neptune's orbit is stable. But now, I'll start working on the farthest corners of this system from the very beginning, and then I'll move on to the closest objects. Now I'll take the dwarf planet Pluto and place it somewhere around here, and also Haumea. Let it orbit somewhere here as well. For now, I'll just place everything randomly like this. Also Eris, let it be somewhere here, and Makemake. And here Ceres will orbit, yes, as well as Pallas and Vesta from the main asteroid belt. I'll also place Sedna somewhere over here. That's all for now. Everything has gone into orbit. For now, everything is on circular orbits, but I'll change these orbits a bit now. I'll give Pluto's orbit a slight tilt. Let it be something like this. Now, regarding Sedna, I want to tilt Sedna's orbit as well. Let it be like this, 14 degrees. And I'll give Eris and Haumea random tilts as well, just so it's more or less like in the solar system. So, as you can see, that's how I set everything up. This is what the outskirts of this newly created solar system look like. These are indeed the inclinations of these various dwarf planets and asteroids. So I carefully combined the largest objects from the Kuiper belt and the main asteroid belt, and let them all rotate together here, just like this. And you can clearly see that Neptune here plays a very similar and important role. So these objects have become like trans-Neptunian objects. And now guys, I won't be able to speed up time too much anymore for the system's stability. So right now I'm near the Sun. As you can see, Mercury is orbiting here. I added it on purpose. That's its native orbit. And instead of Mercury, there will be the planet Uranus here. Next, Saturn will orbit around the Sun. I'll place it at a distance of 1.5 astronomical units from the Sun. If you look at it this way, Saturn ends up in the green zone. But that's roughly on Mars's orbit, roughly speaking. Everything is orbiting normally, it seems stable. I'll add the satellites later. Now the star is Jupiter here, and on its orbit, the first planet will be Mercury. It will orbit at a distance of 0.02 astronomical units. And the second planet here will be Mars. It will orbit at a distance of 0.035 astronomical units. Next, I'll place Earth at a distance of 0.05 astronomical units. And of course, I won't forget the 4 largest moons of Jupiter. These are Ganymede, Europa and Callisto. They will orbit Jupiter, but as full-fledged planets. And in this case, the 4th planet here will be Ganymede. It will orbit Jupiter at a significant distance of 0.07 astronomical units. And then actually here will be Europa. And somewhere around here Io will also orbit, and Callisto will be the farthest away. And the very last planet that will orbit Jupiter will be Venus. And I'll place Venus further out like this. I'll give it an eccentricity of about a value of approximately 0.2. This is the kind of orbit we get. But I'll still move the orbit a bit closer to the main planets, something like this. And I also want to give the orbit a slight tilt, about 13 degrees. Well, let there be this one unusual object in orbit around the star Jupiter. So in the end, this is the planetary system we have around Jupiter. Now, I'll set tidal locking to Jupiter for all the objects except Venus. Actually, it's very easy to do that here. You just need to click this synchronize button. Tidal locking has been successfully set except for Venus. And as we can see, the planetary orbits are rotating stably. I've created a stable system around Jupiter. But now I'm going back to Venus, and I want to give it a moon. Venus's moon will be the moon, and it will orbit Venus at a distance of 50,000 kilometers. And we can see that the orbit is stable, everything is rotating normally. You might ask me, why did you only give Venus a moon? Guys, the answer is very simple. I tried to give both Earth and Mars a moon as well. Most likely because of the close proximity to Jupiter, to the star Jupiter, it simply pulls all these moons away from the planets and captures them into its own orbit. So only Venus managed to keep the moon at a greater distance. As for what will eventually happen to these planets, you'll find out a bit later. Now we already have such an interesting structure in the system, but that's only half the job. Believe me, there's still a lot of work to do here. Let's go back to the Sun. And now it's time to add moons to the gas giants. Actually, unfortunately, we'll have to skip Uranus. I tried adding several moons to it, but because of its extremely close distance to the Sun and most likely also the significant influence of Saturn, all its moons simply get torn away from its orbit, so it will permanently remain without any moons. Saturn's situation with this is a bit better, as you'll see now. So I actually add additional moons to Saturn and then start the simulation. And what are we about to see? That its most distant moons, unfortunately, will actually break away from the planet and go into orbit around the Sun. So I'll have to remove those very distant moons indeed. So I deleted all the distant moons and left only the closest ones. Here are Iapetus Titan. All these well-known ones are orbiting normally here. And by the way, Titan will be interesting here. I want to prepare it for terraforming right away, yes. It will have life here, since Saturn's orbit is basically in the habitable green zone. I'll immediately set its mass to 5 times the mass of the moon, and now let it warm up here, and I'll come back to it later. Now Neptune, I'm adding moons to it as well. We can see that the closest ones have settled into orbit and seem to be rotating normally. What's going on with the more distant objects? Well, for now they're also in orbit, but guys, if I fast forward time, most likely they could break away from Neptune. So, to make the system more stable, I'll remove these distant moons. That's it, those particular moons have been successfully removed. Now only Triton and these other small, close orbiting satellites remain. Now let's move on to the asteroid belt, or the Kuiper belt, I'm not even sure what to call it. Anyway, let's approach Pluto. I'm adding Pluto's moon and the component of its double planet system, Charon. For Haumea, I'm adding its 2 moons, Hyakka and Namaka. Eris has a moon called Dysnomia, but guys, instead of Dysnomia, the moon Titania will actually be orbiting here. So Uranus's moons won't disappear here. I'll set Titania and Oberon as a double component system for some object from this belt. And basically, Titania will be orbiting at a distance of about 10,000 kilometers from Eris. And I'll set up a binary orbit for these 2 objects. Let's check if everything is orbiting correctly. I'll turn on the orbits. As you can see, Titania is orbiting Eris normally, and Eris in turn is orbiting the 2 stars. So everything is great. And I'll set Oberon as a binary component with Ceres. And here, most likely, Oberon will be the primary, because it's larger and more massive than Ceres. Let's set the distance here a bit greater, 15,000 kilometers. And just in case, I'll also set up a binary orbit for them here, in case something gets knocked out of alignment. Well, overall, the binary system turned out well. 1 month passes per second. I won't risk speeding it up any further. Let's check the integrity of the system. As you can see, everything is still going quite well so far. Here, the Sun is closer, Jupiter is rotating normally, as are the planets adjacent to it. Now let's let a decent amount of time pass, so the temperature stabilizes on all the planets, and then we'll continue. Well, a very long time has passed. Throughout this period, no more than 1 month per second elapsed to ensure the most accurate simulation. Believe me, there will be plenty to see. Some interesting planets have turned out there. And as we can see, in the end, Saturn's moon Tethys is leaving the system. Something went wrong with it, so we'll have to remove it. And also, looking up close, I see that Saturn's moon Helene has also broken away, but the other moons are orbiting normally. Well, yes, here Rhea's orbit has gotten a bit off as well. Maybe Titan is to blame here, although it's not so much the orbit that's off, but rather the inclination of the orbit has changed. Well, anyway, this moon keeps orbiting, so everything's perfectly fine. But here, near the gas giant Saturn, we have one crucial unfinished business. We absolutely need to terraform Saturn's largest moon, Titan. Oh, here's how it looks. Let's hide the atmosphere and the clouds. Almost the entire surface of the moon is covered with water, and there are some small scattered islands. So first of all, I'll carefully remove this distinct Titan haze, set it, for example, to Earth's atmospheric conditions, and also make the clouds much more white-toned. Something like this, perhaps. I'll also change one type of cloud to thick clouds. Well, I would really definitely set the opacity level to around 50%, approximately. Let's leave them like that. Now I'll give Titan a strong, good magnetic field, and then I will set the magnetic field strength to 1 Gauss. I will also hide the atmosphere and clouds, and now I will slightly lower the sea level so that there's more land. There are even already places with vegetation, not bad, but as we can see for the most part there is no vegetation. And the pressure is 1.62 atmospheres. The chance for life is just over 3%, which is very little. Now I'll completely add Earth's atmosphere here, apply the preset, but something didn't work, the pressure is still high. But I know what the problem is. I'll have to remove all the water from Titan's mantle. It's all to blame. This is what Titan looks like now. Now I'll just add some water here and everything will be great. See how well it's turning out. The sea level will be somewhere just over 4 kilometers. And so these little islands appear. But still I think we can add a bit more land. Let the sea level be approximately 4.26 kilometers. Ah, that's fine, it'll do. Now I'm updating the atmospheric composition to be more like Earth's. So in the end guys, I created a satellite like this. Overall it looks great. Yeah, the habitability isn't the best, 12%, pressure is almost 1.3 atmospheres and it's nearly 5 lunar masses. And the average temperature is 31.5 degrees Celsius. If you hide the atmosphere and clouds, you can take a closer look yourself. So this is basically what I ended up with. And the last thing I'll do in this system is add rings to the necessary objects and also an asteroid belt. I'm adding a prominent ring to Uranus, a distinct ring to Saturn, and a ring to the dwarf planet Haumea. And there will also be an asteroid belt here as well. It will be like the Kuiper belt in the original solar system. I'll select the asteroid belt, go into the settings, set the inner radius to 20 astronomical units and the outer radius to 35 astronomical units. And now I'm adding this asteroid belt. Here it is, you can see everything, here are these small objects. Let me fly up to one of them. Here's a little rock orbiting here. And there are a lot of these little rocks here. If you point right over here, you can clearly see many of these numerous celestial orbiting objects. So overall the system is built. This is how it looks. Now, let's see what celestial objects we ended up with in this system. First, let's look at the objects that orbit the Sun. The first planet from the Sun is Uranus. Its average temperature is 139 degrees Celsius. And the second planet is Saturn, with an average temperature of -68 degrees. Here's Enceladus, with an average temperature of -120 degrees. On Titan, we've already looked at it, but I'll repeat that its average temperature is 31 degrees Celsius. This is how Saturn looks from its surface at night, not bad. And this is what the Sun looks like from the surface of Titan. And here, nearby, you can also see the second star, Jupiter. Incredible. Though, to be honest, it looks very dim. I decided to update the visuals of Titan's atmosphere a little bit more. It does look nicer this way. Now it's Jupiter's turn, along with its planets. And we'll start by looking at the planet closest to Jupiter. Here we have Mercury. Here, on all the planets except Venus, there will already be tidal locking, I repeat. And in this illustration, we can see that one side of the planet is extremely hot, while the other, on the contrary, is very cold. That is, on the sunlit side of Mercury, the maximum temperature reaches 236 degrees Celsius. And in the area where Mercury is turned away from Jupiter, the minimum temperature drops to -133 degrees. Next is Mars, and it has the same situation as Mercury. It's in tidal lock, and the maximum temperature in the area where the star illuminates Mars is almost 91 degrees Celsius. And in the zone of eternal darkness, although at times the sun might illuminate Mars on the dark side of course, still, the sun gives Mars very little energy here, so we can basically consider this to be a place of perpetual night, roughly speaking. And in these areas the minimum temperature is -208 degrees. Let's take a closer look at Mars. Here we can see what seem to be some bodies of water, and here, let me shine a flashlight so it's easier to see. Oh, look how much water we have here, and there's more water here as well. And what about over there in the southern hemisphere? Is there a little water there? But overall, there's no life at all. Not a very good place for life. And in this part where it's dark, there's nothing special. And here, a lot of some kind of ice has formed in the zone of the Zvezdolaska. Or whatever it's called? Well, yes, that's exactly right. Right here is exactly the Zvezdolaska zone. So that's what Mars looks like. Now here's the appearance of Earth. Here's a clear example of tidal capture. Here we currently have liquid and even some green areas in South America and a little bit in Africa, so it seems quite kind of okay. And even Spain is in a region that's not in perpetual darkness. But on this side, everything is dark. Here, a little bit of light still gets in, but even so, the Earth can't warm up enough here for there not to be ice. If you look at the dark side, there's eternal ice here. And from here, we can see the star Jupiter, while the Sun is way over there. So, let's take a much closer look at the significant temperature differences on Earth here. In this particular spot, the very highest temperature recorded in the ocean is 53 degrees. But if you point somewhere in the majestic Himalayas, it's a frigid minus 200 degrees here. This is the lowest temperature on Earth. And overall, the ambient temperature is quite low in these dark, unlit areas. But if you look at the continents, in South America it's 11 or 12 degrees, and I even find places with 16 and higher. In Africa, it's around 0, closer to the coast. So the temperature varies. As you can see, wherever I move the mouse, you can see the approximate temperature there. It's really cold in Europe. And obviously on such an Earth, the probability of life would be low. The simulator shows that here the probability of life is at 16%. I've landed on Earth, somewhere in South America. The conditions here are normal, and this is how the star Jupiter looks from its surface. Now Ganymede turned out to be very interesting. This side, which is illuminated by the star Jupiter, has warmed up quite well. Here the maximum temperature reaches up to 53 degrees Celsius. And in this area there is liquid water and islands. However, there is no life here. If I hide the atmosphere in the clouds and even make it brighter, as you can see, unfortunately, there is still no life. But on the unlit side, where Jupiter doesn't shine, the temperature can drop even to minus 90 degrees Celsius. Well, Ganymede turned out to be interesting, you have to agree, guys. Now Europa. Here, as we can see, there's nothing interesting. Everywhere Europa is frozen. I'll even show you from all sides. Nothing has really changed. In places where Europa faces the star and is illuminated, the temperature only reaches minus 98 degrees in some areas. And on the other side of Europa, where the star doesn't shine and there's eternal darkness, the temperature drops all the way down to minus 157 degrees Celsius. Next is Io. So, this is what it looks like. You can see its illuminated side. And on this side, where tidal locking occurs, the maximum temperature reaches minus 111 degrees. So there are no positive temperatures here. And on the unlit side, where it's eternal night, the minimum temperature drops all the way down to minus 160 degrees. Let's take another look at the dark side, and as we can see, there aren't really any changes here. But Callisto is kind of interesting. Here, of course, it's illuminated by the sun from this side. And from this side, as I understand it, it's illuminated by Jupiter. It looks interesting. And only here is there a thin strip where nothing is illuminated. Well, you understand, the sun gives very little energy here, which is exactly what you feel there. But on this side, where Jupiter illuminates, there's much more energy. The maximum temperature is listed as minus 13 degrees. That is where Jupiter constantly shines on this part of the planet. And here I'm showing you the dark side. And you can see Jupiter from Callisto's orbit. It already looks quite small. And on the unlit side, so to speak, the minimum temperature can dramatically drop to a frigid minus 75 degrees Celsius, a truly extreme cold. Now I'll hide the atmosphere and clouds. Let's see what's on the surface. Oh, this is even more interesting than I thought. There are some bodies of water that are red in color. This is really fascinating. And it seems like this is vegetation, isn't it? See, there's a green silhouette. I'll fly closer now. This looks like vegetation, some small islands with plants. Incredible. Here's a more detailed look at Callisto from all sides. Even on the dark side it seems like there are these red bodies of water. Ooh, and here, there's even more extensive vegetation present in this particular area. Wow. Even though it's quite a bit of cold on Callisto, guys, there is truly life here. Even on Ganymede, where the conditions are better, life couldn't form. And this life is exactly in the star caress zone. Look, here's the star caress zone. Incredible. And yes, it says here that the probability of life is over 6%. And look, when we turn off the vegetation display, it disappears. Turn it back on and it reappears. Just so you know, guys, this is a realistic simulation, in case you don't believe me. And this red ocean on Callisto is made up of sulfur dioxide. There's quite a lot of it. There's also carbon dioxide in liquid form and ammonia in liquid form. But the highest concentration here is sulfur dioxide, with ammonia in second place. Well, you could say that's why these bodies of water are so red. Because somehow sulfur dioxide ended up here. Not from Io by accident, but it somehow managed to get here. By the way, the pressure here is 1.35 atmospheres, which isn't bad. And as we can see, there's a lot of water vapor in the atmosphere, along with ammonia, carbon dioxide, and sulfur dioxide. There's no oxygen, but as we can see, some kind of exotic life managed to develop here even without oxygen. And now Venus remains. This is what it looks like. It's illuminated by 2 stars, and its average temperature is 70 degrees Celsius. Here, everything is more even, because Venus is no longer tidally locked. The temperature has dropped, but not the pressure, it has remained at extremely high levels. The simulator also shows that Venus has a minimum temperature of minus 28, most likely at the poles. Let's take a closer look at the surface. Well, basically the surface of Venus has stayed the same as it was. I don't see any changes. And on its moon, the average temperature has settled at minus 123 degrees Celsius. Now let's look at Neptune and the distant dwarf planets. On Neptune, the average temperature is minus 207 degrees Celsius, and on its largest moon, Triton, the average temperature is minus 226 degrees. The hyperdwarf planets in this system. Let's start with Pluto. On Pluto, the average temperature is minus 217 degrees Celsius, and on its companion Charon it's minus 221. Now Irida and Titania. Irida has an average temperature of minus 205 degrees, and on Titania it's also minus 205. Now let's look at Oberon and Ceres. On Oberon, the average temperature is minus 214 degrees, and on Ceres the average temperature is minus 213. And the other objects from this belt. Haumea, the average temperature there is minus 211. Makemake is minus 208, Pallas is minus 215. Vesta is minus 214, and Sedna has an average temperature of minus 221 degrees Celsius. That's how I reimagined the solar system. That's exactly the idea that came to my mind. Give it a like if you enjoyed it, and also leave a comment letting me know what you think of this version of the solar system. And if I made a mistake somewhere or missed something, let me know in the comments. Thank you very much for watching, and see you again in the universe.